In previous video, we covered the definition of region of constraint, and I showed you through example 1 how do we find the region of constraint for a linear programming problem. On my notes, I have a guideline for linear programming. I'm not going to copy the words on here. I will just read it. You can find them in my notes. It's in Moodle. Linear programming has 3 steps in the procedure. Step 1, identify variables. Sketch feasible region. That's what we have done in example 1, right? Step 2, identify the objective function that is to be optimized. We're going to see that concept in example 2. Step 3, evaluate the function at each of the vertices of the feasible region and compare the values found. If the feasible region is bounded, the optimum value means either maximum or minimum. The optimum value of the function will occur at a vertex. If the feasible region is unbounded, the optimum value of the function may not exist, but if it does exist, it will occur at a vertex. Step 3 tells us how do we find the maximum or minimum value for the objective function. For the details of the guideline, please refer to my notes. For the sake of the time, I didn't copy them here. But we are going to apply that guideline for example 2. Let's see example 2. Find the minimum and maximum values of the given functions subject to the given constraints. Let's look at the number 1. The linear programming problem normally has 2 parts. Part 1 is the objective function, your goal, the function that you are going to optimize, either maximized or minimized. So here the objective function is given. It depends on 2 variables. This actually is a multivariate function. Multivariate function means the function has more than 1. So here is 2 independent variables. So just let you know, this is a function, but it's a multivariate function. It has 2 independent variables. The value of the function depends on x and y together. Depends on both x and y. So the objective function is 6x plus 10y. For the 2 variables x and y, we have the following 3 constraints. Second part of the linear programming are the constraints. So in example 1, I have showed you how do we graph the feasible region, right? So what's the guideline say? The guideline, step 1 of the guideline is to graph the feasible region. So let's do that. We're going to graph the feasible region. X is non-negative, y is non-negative. That tells us the graph is going to be just in quadrant 1. Let's graph this inequality first. Let's graph the solution set of that inequality first. What's the boundary of that inequality? 2x plus 5y less than or equal to 10. If we change the inequality symbol to equal sign, we have a straight line. That means the solution set of the inequality has a boundary, which is a straight line. And the straight line right now is in the standard form, right? Standard form is more convenient when we graph them. Most of the cases, it's more convenient just to find the x-intercept and the y-intercept to graph it. All right, so if x equals 0, you can see the convenience, how easy this becomes. As x equals 0, this one disappears, right? As x equals 0, 5y equals 10, so y equals 2. Do you see that? 5y equals 10, of course y equals 2, right? So we found the y-intercept 0, 2. This time we let y be 0. If y be 0, then this term disappears. We would have 2x equals 10. Divide both sides by 2, x equals 5. X-intercept, y-intercept. Let's plot the 2 points. 5, 0. Let's see 5 is here. This point is 5, 0. If that's 5, then 1, 2, 3, 4, 5. 1, 2. And 0, 2 would be around here. If we connect the 2 points, we would have the boundary line for the inequality. Are we going to draw the boundary line solid or dashed? We're going to draw it solid because, again, we have seen this like over and over. The inequality symbol is less than or equal to. So the points on the boundary also solutions of the inequalities. So let me use black again here. I connect them. I'm drawing a line segment, all because up front I see that the variable x and the variable y are non-negative. But actually, when we only think about the inequality, solution of the inequality, this inequality, the solution, the boundary would be a straight line. It's extending, okay? It's extending. It's extending. And the boundary divides the whole plane into 2 parts, the half plane above and the half plane below, right? And by choosing a testing point, we would know the solution set is the plane, half plane below or half plane above. That is 0, 0. If we plug in here, we would have 2 times 0 plus 5 times 0, that is 0, 0 less than or equal to 10. It is a true statement. Means 0, 0 satisfies the inequality. 0, 0, this testing point is the solution of the inequality. So the solution set of the inequality, this inequality, is the half plane below. Let me repeat it. The solution set, hold on, I don't know how do I just get rid of the advertisements. The solution set of this inequality is the region, is the half plane below the boundary line, including the points on the line. Okay, we are done with this one. Let's see x bigger than or equal to 0. Some of you might know what does that mean, but we're gonna apply the process, the standard process to find the solution set for that inequality. X bigger than or equal to 0. That's an inequality. Y doesn't show up because the coefficient of y equals 0. If we find the boundary for the solution set of the inequality, we would have a vertical straight line. What is that vertical straight line? Y-axis, actually. Okay, that is a y-axis. And we're going to draw the line solid. Same reason, because the original inequality has equal sign in it. And this straight line divided the whole plane into half. Half plane to the left, half plane to the right. On which part? We can try 5, 0 here. We can try this point. Because this point is so convenient, it's already there, and it's to the right of the, it's not on the boundary. So if we plug in x equals 5, 5 bigger than or equal to 0, that's a true statement, right? So that means 5, 0, this testing point is is a solution of the set. So the solution set of this inequality is the half plane to the right of the y-axis, including the points on the y-axis. One more time, the solution set of this inequality, x bigger than or equal to 0, is the half plane to the right of the origin, including the points on the y-axis. The last one, y bigger than or equal to 0. The inequality is y bigger than or equal to 0. Boundary is a horizontal straight line. The horizontal straight line actually is the x-axis. X-axis. Okay? And we can find the testing point. This time maybe we can just use 0, 2 because it's already there. 0, 2 is a point not on the boundary. So if we plug in y equals 2, we got a true statement. So that means 0, 2 is a solution of this inequality. That means the solution set of this inequality is the half plane above the x-axis. Half plane above x-axis, including the points on the boundary on the x-axis. So let me repeat the three solution set. Solution set of this inequality, the whole half plane below the slant straight line, including the boundary, the points on the boundary. The solution set for x bigger than or equal to 0, all the points to the right of the y-axis, including the points on the y-axis. Solution set for y bigger than or equal to 0, the whole half plane above x-axis, including the points on the x-axis. So if we graph the solution set of the system, that's a system, right? The system includes all the three inequalities. The feasible region is this region, is this triangle region, including the boundary. That's the first step. Then how do we maximize and minimize the objective function? What's the guideline say? What does the guideline say in second step? Step 2, identify the objective function. That is a given already. We don't have to identify. Sometimes you do if the problem is more complicated. This is very straightforward. Step 3, evaluate the function at each of the vertices of the feasible region and compare the values found. If the feasible region is bounded, the optimum value of the function will occur at a vertex. So the feasible region is bounded in this case, right? How many vertices? I need to find the color blue. How many vertices the triangle has? Of course, 3, right? This one, and this one. The coordinates of this vertex is 5, 0. 0, 2 is this vertex. 0, 0 is this vertex. We have 3 vertices for the region, triangular shaped region. We are going to evaluate the objective function at those 3 vertices. Okay. Objective function, let me copy it again here. F of x, y equals 6x plus 10y. In the first, it doesn't matter the order. So you want to try f of 0, 0 first in this vertex 0, 0. Then we would have 0, of course, right? Plug in x equals 0, plug in y equals 0. Of course, the value of the function is 0. Let's try 0, 2 this time. 0, 2. X equals 0. Y equals 2. What do you have? Do you have 20? So the value of the function, of the objective function at this vertex is 20. The last one, 5, 0. X is 5. Plug in. Y is 0. Plug in. 6 times 5, 30. So the value of the objective function at this vertex is 30. We went through all the 3 vertices. By the guideline, the maximum and the minimum value of the objective function must occur at the vertices, right? So which value is the smallest value? Of course, this one. And this is the biggest, right? So we can make a conclusion. The objective function reaches the maximum value 30 at vertex 5, 0. The objective function reaches its minimum value, which is 0, at the vertex 0, 0. You can repeat the video for what I just said. There are two things might be confusing. Is the maximum value of the objective function and the point at which the function reaches the maximum value. Okay, so it's different. 30 is the maximum value of the objective function. The function reaches that maximum value at 5, 0. Same thing with the minimum value. The minimum value of the function is 0. The function reaches that minimum at the point 0, 0. So two different things. Optimum, and versus the point at which the function reaches the optimum. So do you see what I'm saying? One is the optimum, either maximum or minimum. The other is the point at which the function reaches its optimum. There are two different things. When you do the day quiz of this section, be very careful. What's your goal? What are you looking for? Are you looking for the optimum or the point at which the function is assumes the optimum? Very important. Let me see how many minutes right now. 17 minutes. Let me cover the next problem in part 3.